Before we begin, I'd like to draw your attention to the picture that's being projected. This picture is a tribute to Ada. It was created by the children of Botley Primary School's Code Club. It was arranged by Peter Lister. Thank you very much, Peter. Parents of a certain age will recognise that this was implemented in a system called Minecraft. Minecraft is a plot to steal the souls of all the 10-year-olds in the country, and I speak from experience. But a lovely tribute by the children of Botley Primary School. So we have a couple of talks. We have a couple of talks this afternoon. Firstly, it's my pleasure to introduce all the way from California, Judith Grabiner from Pitzer College. She's going to talk about mathematics and culture. Judith.
Thank you. I want to thank Ursula for inviting me and asking me to speak about mathematics and culture. And secondly, I want to start by saying there will be an introduction. So, where's the device that advances the slides? This is it. Okay, this is it. Okay, good. All right, I want to argue today that geometry interacts with all aspects of human thought and life. Now, every mathematician has some sort of relationship with Euclid, and in my token reference to Ada Lovelace, she began her studies of mathematics learning geometry and told her tutor that she could only understand a proposition when she could see the figure in the air. Now that's a very good line, and it also serves for me as a transition, because geometry has long been thought of as the science of space. So what is space? Does space exist? What's its nature? The history of these questions involves a lot of important thinkers and artists and really the entire universe, and that's what I want to do today. Now, Euclid is special. When we use terms like truth and proof, we're channeling Euclid. For 2,000 years, Euclid's geometry seemed to prove truths about geometrical objects and thereby to achieve certainty. Now, Plato thought that geometry was true and certain because the subject matter was eternal and helped to draw the soul from the imperfect world of change to the changeless eternal truth. But Aristotle said, no, the truth and certainty of geometry comes from the way it's put together, using logical deductions from explicit, self-evident assumptions and clear definitions. Euclid probably looked over his shoulder at Aristotle's criteria while he was writing the Elements. And many important later thinkers believed that other subjects might come to share the certainty of geometry if only they followed the same method. For instance, Descartes said, if we start with self-evident truths and then proceed by logically deducing more and more complex truths from these, why, he says, in effect, there's nothing we couldn't come to know. Well, following Descartes, Benedict Spinoza wrote a book, An Ethics Demonstrated in Geometrical Order, with explicitly labeled axioms and definitions, and including theorems like this one, quote, God, or substance consisting of infinite attributes, necessarily exists, end quote, whose proof he has several proofs. He closes them with a QED. Now, the influence of the Euclidean ideal on science is clear from Isaac Newton's mathematical principles of natural philosophy. As you see here, Newton called his famous 3 laws of motion axioms, and he deduced even his law of gravity in the form of explicitly stated theorems. And Newton famously said, "It is the glory of geometry that from so few principles it can accomplish so much." One more example. The American Declaration of Independence is an argument whose author tried to inspire faith in its certainty by using the Euclidean form. Thomas Jefferson, who knew more of the mathematics of his time than any other American president, began his argument thus. See, in the United States, people wouldn't laugh at that. Jefferson began, "We hold these truths to be self-evident, that all right angles are equal." Oh no, that's not what he said. But that's what it sounds like. Another self-evident truth in the Declaration is that if any form of government fails to secure human rights, it is the right of the people to get rid of it and set up a new government. The Declaration asserts that King George's government does not secure these rights. Then it says, to prove this, let facts be submitted to a candid world. And once the facts have proved this, then we've got if P then Q, P, and therefore Q. Thank you. Computer scientists, I mean, you're supposed to know this. All right, once the facts have proved this, the actual declaration that founded the United States is stated explicitly as a conclusion of a logical argument, beginning with a therefore, which in one of the original printings is italicized, as I have it here. So, in philosophy, theology, science, politics, the idealized Euclidean model of reasoning has shaped conceptions of proof, truth, and certainty. Okay, that was the introduction. Now, for the first half of the actual talk, we'll look at Euclid's elements, at the idea of Euclidean space, and some important related ideas, and their wide-ranging influence, and we'll see that it lives up to its press notices. But we'll also see that there was a problem. And in the second half of the talk, we'll see that the problem and its resolution have produced a non-Euclidean world, and that this break with the past has had a comparably great impact. Okay, so here we go with part one. These are Euclid's postulates, hopefully the minimal set of self-evident truths from which all the true results of geometry can be logically deduced. Well, postulates 1 through 4 are pretty straightforward. I hope no one wants to argue with them. But look at number 5, Euclid's so-called parallel postulate, which you will observe does not mention parallels at all. That one's complicated, so I think we'd better draw a picture. Sort of retain in your mind how that struck you when you saw it. Here's a picture. What postulate 5 means is if the two green lines are cut by a third line, AB, such that angle A and angle B add up to less than 2 right angles, then the two green lines eventually meet on that side. Now I ask my students to vote on whether this postulate is self-evident. And they overwhelmingly vote that it is not. Some of them don't understand it after 2 runs through. And you got to draw a picture. The ancient Greeks agree with my students, and that is the problem that I mentioned. Okay, well, if this postulate is not self-evident, then maybe it can be proved from the other postulates. So the Greeks tried to do this for reasons that the mathematically literate will recognize. They did not succeed. And so, also trying, did the best mathematicians in the medieval Islamic and Jewish worlds. Then mathematicians in Christian Europe on into the 19th century, including John Wallis, whose views on this subject are actually in a poster out in the lobby. On into the 19th century, pretty important famous people. Now, while trying to prove postulate 5, one thing that the Greeks proved right at the beginning is that Euclid's postulate is logically equivalent to the uniqueness of parallel lines. That is, given a line, then a given point in the same plane, there's only one parallel through that point to that line. It's a common alternative postulate found in many textbooks, including the one by John Playfair in the 18th century, hence it's called Playfair's axiom, if you care. Now, Euclid defined parallel lines as lines in the same plane that never meet. From his first 4 postulates, he can prove a lot of cool stuff, like that parallel lines can be constructed. But he needs that problematic 5th postulate, which he uses very rarely, for his proof of one key theorem. If 2 parallel lines are cut by a third line, the alternate interior angles, like angle 3 and angle 6, and the corresponding angles, like angle 2 and angle 6, are equal. From that theorem, Euclid proves not only the uniqueness of parallels, but many other theorems that involve parallel lines, like that they're everywhere equidistant. We expect this of decent parallel lines. Or that the sum of the angles of a triangle is 2 right angles. But Euclid doesn't talk about space. Nevertheless, starting in the Renaissance, people talk a lot about space, an infinite homogeneous space that's the same in all directions and in which every point is just like every other point. This is the space that Euclid's geometry happens in. And the role of philosophy in describing that space turns out to be really, really huge. The idea that space must be the same in all directions comes from what is called the principle of sufficient reason. For everything that is, there's a reason why it is as it is and not otherwise. That sounds pretty trivial. Turns out not to be quite so trivial. Principle's at least as old as Archimedes. Here's what Archimedes does with it. Have a lever with equal weights at equal distances from the fulcrum. It has to balance. Why? Why not? Because there's no reason for it to go down to one side or the other, because the sides are completely equivalent, and that's why the symmetric lever necessarily must balance. Furthermore, this principle of sufficient reason explains why space is infinite. Giordano Bruno said, space must be infinite because there's no reason for it to stop at any particular point. All the points are the same. The greatest advocate of the principle of sufficient reason was Leibniz. Leibniz said it's the principle of sufficient reason and the laws of logic that God used in making the universe. God made the universe optimal in the best possible way. Many scientific laws still use the language of optimization, like that light is refracted in the least possible time. Now, for Leibniz, sufficient reason gives us the simplest scientific laws and the best possible laws in the universe. And if the principle of sufficient reason is true, the universe is transparent to reason. God made it rationally, so we humans can figure it out. And here is one striking example. Consider Newton's first law, which was first formulated 50 years before Newton, independently by Descartes and Pierre Gassendi. And here's how they found it. First law of motion says a body with no forces acting on it continues in a straight line at a constant speed. Why? Well, it goes in a straight line because every direction is the same, so there's no reason for it to turn to the left or to the right. It goes at a constant speed because every point's the same, so there's no reason for it to prefer this point to this point and speed up to get there. And you can see that the same argument can be made why a body that is at rest with no forces acting on it stays what it is, where it is. Okay, now back to parallel lines. The great mathematician Joseph Louis Lagrange decided that he could prove the uniqueness of parallels, logically equivalent to Euclid's fifth postulate, by using the principle of sufficient reason. Okay? Well, this is what he's trying to prove, the uniqueness of parallels. Oh, wait a minute. Who says you can use the principle of sufficient reason in a mathematical proof? Lagrange says so. He says it is just as obvious and true as are the laws of logic. And I hope I convinced you in that little brief thing I said that it was all over science in the 18th century, principle of sufficient reason. I found this manuscript in which Lagrange does this. I think it's really, really interesting. He's going to prove this. He's going to prove that theorem, and it's a proof by contradiction. Given that we have one parallel through point P, which we have here, suppose there were another parallel. The original line through point P might look like this. But by the principle of sufficient reason, there's no reason that the new parallel line should be below the point P on the left and above it on the right. It could equally well be drawn the other way. So, principle of sufficient reason says there must be another symmetric parallel line that goes the other way, as in this new diagram. Okay, Lagrange then repeats this exact same argument for lines symmetric to his new parallels. So, for instance, you get a third line on the other side of his new parallel, and it looks like this. And so on, lots and lots more. And I will show you Lagrange's own picture of the final situation from his manuscript, which Lagrange says is absurd. So he concludes there can only be one parallel, QED. Now, Lagrange never published this manuscript. Maybe he came to see that when he used the principle of sufficient reason at the beginning to produce the first set of new symmetric parallels, that he was assuming that, this one here, he was assuming that the original two parallel lines were everywhere equidistant, and thus assuming the very Euclidean nature of space that he was trying to prove. But the fact that a great mathematician like Lagrange got up in public at the Institut de France and linked space being Euclidean with Leibniz's principle of sufficient reason demonstrates how closely linked sufficient reason was with the necessity of space being Euclidean. Oh yes, and space has to be real. Newton insisted on that. Why? So he can distinguish real accelerations, that is, accelerations with respect to space, from apparent accelerations. Real accelerations involve real forces. So from real acceleration, like a falling apple or a planet orbiting the sun, real accelerations require forces, and thus he can show that gravity is a real force. Furthermore, that real space for Newton's physics turns out to be Euclidean. Why? Well, one reason is that you have to use parallelograms of force all over Newton's physics, and proving the properties of parallelograms requires Euclid's theory of parallels and therefore postulate 5. Well, okay, that's Newton. There's another guy. Whoops, wrong guy. All right, I'm sorry, I thought I had a picture of Leibniz again, but I didn't. Leibniz disagreed with Newton about space. Leibniz essentially says there is no such thing. Space is just the relations between bodies. But Newton's view prevailed. Why? Okay. Listen to Leonhard Euler. Euler says, the straight line, constant speed motion of a single body with no forces acting on it, according to Newton's first law, that can't possibly depend on where other physical bodies just happen to be at some particular time. It's got to be a straight line always. Therefore, a straight line not with where all the bodies happen to be right this second, but with respect to something that doesn't change, namely space. So space has to be real and Euclidean. Why did mathematicians of the 18th century want so much to prove the parallel postulate? Well, precisely because it was so important in establishing the correct nature of space, not just for geometry, but all of science rested upon it. And now to philosophy. A super influential philosopher, Immanuel Kant, agreed with Newton that space exists, agreed that we have to order our perceptions in space, but Kant said space exists in our minds. And we each have the same unique space in our minds. And it turns out for Kant that this space, too, has to be Euclidean. And let me explain, because he obviously never says this, because it never occurs to him that there is a non-Euclidean alternative. All right, to argue that we can come to know non-trivial truths about non-material things, technically synthetic a priori judgments, Kant uses Euclid's proof that the sum of the angles of a triangle is 2 right angles. If it's been a long time since you did this, I will remind you how Euclid's proof goes. You start with a triangle. Well, you can't add the angles. They're in different places. So to do the proof, first thing you do is you extend the base to D, and then you construct a line through the corner parallel to the opposite side, so CE is parallel to AB. And then you prove the equality of various angles in the new diagram to the angles around C, because the angles around C obviously add up to 2 right angles. This is the proof. The equal angles are specified in this slide, but it isn't the details of the proof that matter. Kant's key point is this: the proof cannot work unless and until you make those constructions. Okay? Well, where'd you make those constructions? Not on paper. Geometry isn't about physical angles. You made them in space, he said, the space in your mind. So, space. Now, the proof needs the results that if 2 lines are parallel, the alternate interior and corresponding angles are equal. As I said before, Euclid's proof of that theorem explicitly requires the fifth postulate. So this theorem about the sum of the angles requires space to be Euclidean. Now Kant doesn't say this, but he does say there's only one space, just as there's only one time. So for Kant, no alternative to Euclid seems conceivable. Well, Kant's pretty heavy. Let's pick somebody lighter. Whoops. There you go. One more philosopher witnessed to Euclidean space as truth. Voltaire shared the widespread 18th century idea that universal agreement was a marker for truth. And he said, Voltaire, there are no sects in geometry. One doesn't say, I'm a Euclidean. Demonstrate the truth, he says, and the whole world will be of your opinion. Mathematics exemplifies this for Voltaire, and he wants ethics to do it too. Voltaire wrote in my favorite Voltaire quotation, quote, there is but one morality, as there is but one geometry. And I said that in class once, and one of my students shot back, wrong on both points, Voltaire. The art and architecture of the early modern period also reflect the Euclidean nature of space. Art and architecture reinforced the Euclidean intuition of space in the minds of everybody who looked at the paintings and lived and worked in the buildings and public squares from the Renaissance well into the 19th century. Perspective in art, which is based on Euclid's geometry, helped make people literally see space as Euclidean. And let me illustrate a bit. One of the most important early perspective paintings of the Renaissance here, the Trinity by Masaccio. We are used to two-dimensional pictures that look three-dimensional. It's three-dimensional because we've got photography and television and iPhones and all sorts of wonderful things like that. In the Renaissance, they didn't. So a painting like this, as the quotation from Vasari makes clear, was incredibly exciting to them. And the realistic illusion of depth in Renaissance art comes explicitly from geometry. Useful briefly to look at a couple of medieval works of art to appreciate the difference between medieval and Renaissance art. Pick a couple of things I like. The Bayeux Tapestry, the people are the same size as the castle. This is Nicholas of Verdun, the crossing of the Red Sea. Well, the people are as big as the whole Red Sea, which is also red. It's this wonderful art, but there's no convincing three-dimensionality. Okay, now in the Renaissance, we're going to move into a different kind of space. It's pretty dramatic contrast. Okay, the geometry used in creating Renaissance art is literally Euclidean. It comes from Euclid's elements of geometry and Euclid's optics. Here's a theorem from Euclid's optics, not Euclid's diagram. I think you see the truth of the result. And here is something from Euclid's elements. If a straight line is drawn parallel to the base of a triangle, it cuts the other two sides proportionally. That theorem is just essential to the Renaissance geometric theory of perspective. Here's how the geometry lets you see three-dimensional reality on a flat canvas. This is known as the Alberti construction. What you got there is a square floor divided into squares, and the plane of that floor is perpendicular to the plane of, in this case, the screen. This photograph does the Alberti construction for two parallel railroad tracks perpendicular to the plane of the screen. Now the checkerboard construction of Alberti's, let's just take a quick look at it again, checkerboard, okay, was used by many Renaissance painters because you have the squared off pavement and it emphasizes the perspective and also helps the artist draw it. So this is supposedly a religious picture about Christ, but I look at it as an application of the checkerboard. Here's another artist you've probably heard of doing the same thing. The checkerboard here is on top. These are artists who were also mathematicians, Piero and Leonardo da Vinci. Moving north from Italy into Germany, here's another mathematician artist, Albert Dürer, showing you precisely how to construct the image. Well, okay, you're a Renaissance artist. Do you have to master all this mathematical theory to draw in 3 dimensions? Not at all. Just find the right books. This is Schern is a student of Dürer's, and he says, Just look at my drawing, then you'll know what to do. Here's another German. I like this picture by Count Johann because it literally embodies Euclid's theorem about the proportional sides of similar triangles. One more Renaissance painting. This is so great. Okay, in sum, the objects in the painting look the way an objective observer would actually see them, in a rational order created by Euclid's geometry. The art helps to teach us to see our world as Euclidean. Also, architecture teaches us to see our world as Euclidean. Okay, whenever I talk about this, I'm always in a room like this one, full of parallel lines. Look at the sides of this auditorium. Full of parallel lines which are everywhere equidistant, which make equal right angles with the floor. The banister kindly lets us look at them making equal non-right angles with a transversal, all with the properties that Euclid used to prove his fifth postulate. This is the kind of room that you would design if you wanted to brainwash people into believing that space has to be Euclidean. So, here's the 18th century world, the world of sufficient reason. It's symmetric, it's balanced, it's based on self-evident and necessary truths. It's embedded in Euclidean space. We can figure it all out rationally by ourselves. Euclid's geometry is the universally agreed upon model of perfect intellectual authority. That is the end of part one of this talk. Now we'll blow it all out of the water. It's really amazing that in the early 19th century, Gauss, Bolyai, and Lobachevsky, the three independent inventors of the first non-Euclidean geometries, were able, in spite of all this Euclidean brainwashing, to imagine that space could be other than Euclidean. Now what they did was to realize that the absurd consequences of denying Euclid's postulate, consequences like parallels are not unique. Parallel lines, that is, lines that never meet, do not have to be everywhere equidistant. These consequences are not absurd at all, but are truths in some alternate, counterintuitive reality. Well, let's stick for the moment to two dimensions, a surface. Here's a modern non-Euclidean surface that obeys Euclid's first four postulates, but disobeys his fifth. Notice that the red and yellow shortest paths never meet. They're parallel. They're both parallel to the blue one. Notice that they intersect. So we got two parallels through the same point. And notice that those three parallel lines, the red, the yellow, and the blue, are not everywhere equidistant. The idea of non-Euclidean geometry was so revolutionary that Gauss never even got up the nerve to publish his work on the subject. Non-Euclidean geometry required a paradigm change, realizing that the logical implications of denying Euclid's postulate were not intellectual absurdities, as Lagrange had thought, but part of an alternate reality. And of course, the Lobachevskian version of non-Euclidean geometry with space of negative curvature was not the only one. There are lots more non-Euclidean manifolds, including some of positive curvature, as was explained to mathematicians, notably by Riemann. But what about all that stuff that Kant said? That space is in the mind, and that the properties of space are the same for all human beings, and that we order all our perceptions in space. Kant's space was Euclidean, all right? We can't possibly order our perceptions in a non-Euclidean space. Can we? Yes, said Hermann von Helmholtz. Of course, in order to do this, we have to divest ourselves of 2,000 years of Euclidean experience. But if we can order our perceptions in a three-dimensional non-Euclidean space, Kant is wrong. And if Kant is wrong, says Helmholtz, the postulates of geometry are not dictated by the nature of the human intellect or by logical necessity. Whether space is Euclidean or not is a question for experience. So I challenge you, let's see if through new experiences you can learn to order your perceptions in a non-Euclidean three-dimensional space. Here we go. You probably have a convex mirror on your car, and there's a warning on it. Warning. The space you see in this mirror is not Euclidean. See the parallel lines in the top and bottom of the bookcase not being everywhere equidistant? Now, yes, you can learn to order your perceptions in such a space if you have made it so far with your car. I salute you for having done so. But you might say, look, it's just a mirror. It's an illusion, the world in the mirror. Only our own world, the Euclidean world, can possibly be real. Oh, yeah, says Helmholtz. Look, imagine you're having a dialogue with the guy in the mirror. You say, my world is real. Yours is distorted. He says, yeah, how can you tell? You say, well, in your world, when you get closer and closer to the mirror, you grow bigger. When you get farther and farther away from the mirror, you get smaller. This violates the obvious Euclidean fact that when you move something around through space, it stays the same size and shape. Guy in the mirror says, really? Yeah, let me try that. So he takes a yardstick. He comes up to the interface between his world and ours, and he measures himself. I'm 6 feet tall. And he goes to the back of the room, away from the mirror, and he measures himself again. No, you're wrong, he says, I'm still 6 feet tall. And you say, well, your yardstick changed its size also. And he says, come on, Jack. Helmholtz says, there is no geometrical experiment that you can do that will decide the question of which one of these worlds is the real one. And by the way, if that sounds like relativity theory, it's no accident. I was going to say a straight line, but I shouldn't use that word. There is a line of historical influence in German philosophy from Helmholtz to Ernst Mach and then on to Einstein. The British mathematician philosopher W.K. Clifford argued that the new geometry was a revolution like the Copernican revolution. He said, it used to be that the aim of every scientific student of every subject was to bring his knowledge of that subject into a form as perfect as that which geometry had attained. But no more. Before Copernicus, said Clifford, people thought they knew all about the whole universe. Now we only know one small piece of it. Likewise, before non-Euclidean geometry, the laws of space and motion implied an infinite space whose properties were always the same. No more, said Clifford. Okay, space appears flat and continuous, but only as far as we can explore, and no farther. Well, here is an even more radical view. Poincaré also saw the new geometries as revolutionary, but he disagreed with both Kant and Helmholtz. If, as Helmholtz said, geometry comes from experience, then geometry would not be an exact science. Still, Poincaré knows that we have more than one kind of space in our minds. He's on the other side of the non-Euclidean revolution. So the postulates of geometry are not synthetic a priori intuitions, as Kant said. They're not experimental facts, as Helmholtz said. And they aren't necessary self-evident truths, as Voltaire and Lagrange said. Geometrical axioms, says Poincaré, are conventions. Okay, so how should we decide which set of axioms to use? Those of Euclid, Lobachevsky, or Riemann? Poincaré says our choice among these conventions can be guided by experience, but as long as we avoid contradictions, our choice remains free. What are we to think of the question, is Euclidean geometry true? The question has no meaning. We might just as well ask if the metric system is true and the old weights and measures false. One geometry cannot be more true than another. It can only be more convenient. In the 20th century, it turned out that non-Euclidean geometries of the Riemannian type, that's the positively curved space, were in fact more convenient because Riemann's type of geometry is what Einstein needed to do general relativity. According to Einstein's theory of gravity, the paths of planets moving under gravity are shortest distances in a non-Euclidean manifold. Light no longer travels in Euclidean straight lines, but shortest distances again in a non-Euclidean space-time manifold. Is real space really Riemannian? Poincaré would say, that's what works. You know, though, if we're really interested in what works, we also ought to study empirically how people actually perceive space. And even before non-Euclidean geometry, philosophers like Bishop Berkeley pointed out that we don't see distance at all. What we see are angles. And we infer the geometry of what's out there from the angles we actually see. I'll give you a really easy example. If I asked you about this, you'd say, oh, look, 3 90-degree angles are coming together. But look at what you actually see, the 3 120-degree angles coming together. Our visual space isn't the same as the space that we claim to see. And the invention of non-Euclidean geometry really made psychologists think a lot about things like that, like Helmholtz. Helmholtz did an experiment where he asked people in a dark room to arrange little points of light along a table. He wanted them to do 2 parallel lines going away from themselves. So the people made the lines out of the little points of light, and then he turned the lights back on, and you could see that the lines weren't parallel at all. They curved away from the observer. And so Helmholtz concluded, space, our perceptual space is Lobachevskian. But psychologists have done many more experiments, and turns out the space of visual perception isn't represented by any consistent geometry. That's depressing. Now, this is all European material. The cultural linguist Stephen Levinson has shown that people in many different cultures have other ways of ordering their perceptions than in an external Euclidean space. Some cultures do use the idea of a fixed coordinate system in space with 4 cardinal directions, as when you say the car is to the south of the building. That's like Newton's framework. But other cultures order their perceptions in space more in line with Leibniz's ideas, the relation between bodies. Some from the individual point of view, as if you say the car is to the right of the building. You're in that, okay? Or you can get the individual out of it entirely and just talk about the intrinsic properties of the objects, as if you say the car is in front of the building. In our own culture, GPS navigational systems are changing people's supposedly innate intuitions of space from the Newtonian to the Leibnizian. Once I asked a taxi driver in Maryland if his GPS system had changed how he thought about space. He was a smart guy. He thought that was a really cool question. And I wrote down what he said. Here's what he said. I used to have the whole geography of greater Baltimore in my head. I don't anymore. Like when I take you somewhere, I'll turn left out of the airport. I'll take the expressway to your exit, then I'll turn right. When I leave you off, I'll just reverse that. I'll turn left. I'll get on the expressway. I'll turn right into the airport. I'll get back. But I won't know where I've been. Well, okay, let's get back to the paradigm shift from Euclidean geometry to non-Euclidean geometry. I'll start with a classroom anecdote. Gotcha. Okay, once I passed a convex mirror around in class, and one of my students looked at himself in the mirror and he said, "This is distorted." And somebody else said, "You're a Euclidean chauvinist." So what do modern theorists of culture have to say about this paradigm shift? One especially interesting thinker on this topic was José Ortega y Gasset. Ortega used the new geometries to argue that provincialism, assuming that our own experience or values are universal, is wrong. He sounds like Clifford here. Euclidean geometry is provincial. It was an unwarranted extrapolation of what was locally observed to the entire universe. Instead, Ortega says, reality organizes itself to be visible from all viewpoints. Einstein's theory of relativity promotes the harmonious multiplicity of all possible points of view, not just for mathematics and physics, but also for politics and culture. There's a Chinese perspective, Ortega says, that is fully as justified as the Western. Okay, now briefly to architecture. Take Zaha Hadid, the first woman to win the Pritzker Architecture Prize. As an undergraduate, she specialized in mathematics. Notice we aren't in the Renaissance ideal city anymore. There's more. Here's what she says about the world of the 21st century. The most important thing is motion, the flux of things, a non-Euclidean geometry in which nothing repeats itself, a new order of space. And the new geometries inspire many other types of artistic freedom. I'm going to run by rapidly 3 examples from Cubist art of what Ortega called reality organizing itself to be seen from all points of view. Tea time. I'm in England, you know. Look at the teacup. The guitar. A portrait by Picasso. Planes and angles from multiple points of view. Notice he's not the guy in the picture is not in a visually graspable 3-dimensional space at all. A different kind of geometrical influence on art. Plaster models like the ones in your building. This is all we got in Claremont, but you got lots more. mathematicians use these to teach and study the geometry of non-Euclidean surfaces. Let me show you some art inspired by such models. That's the world. The name of this one makes clear that it comes from geometry. And you remember the helix from the thing I just showed you? Here's just a lovely piece by Man Ray. It's just beautiful. The plaster models that Man Ray studied were the ones in the Poincaré Institute. Man gets his credit, Poincaré, in Paris. Man Ray was just blown away by them. He said these shapes were so unusual, as revolutionary as anything that is being done today in painting or in sculpture. One more of many examples. I find this charming. So, artists are influenced by the new geometry. They cite its authority and its prestige on their own behalf. They use it as part of their creation of self-consciously modern art, and they help us see a different world. Coming now to my last pair of slides. Here's the first. I found this searching Google image for hyperbolic paraboloid. And I like this picture a lot because it shows us how much non-Euclidean geometrical objects had become part of the general culture already more than half a century ago. And here's one that became famous much more recently in your own country. The roof is another hyperbolic paraboloid. Okay, so you're entitled to conclusion. Conclusion. Twice in history, first in Euclid's world, and then in the non-Euclidean world, ideas about geometry have helped shape art and architecture and science and philosophy, and have helped shape the way people see and think about the world. I hope that this talk, and in fact this entire conference, help a wider public better understand the intimate relationship between mathematics and culture. Thank you very much.